Hello, today we're going to talk about energy diagrams. Okay, so a lot of this is review from Unit 5. Exothermic reactions, the reactants are starting at a higher energy level than the products. So it must be releasing heat to the surroundings. The activation energy is, of course, the distance between the difference in energy between the reactants and the activated complex or transition state. This is also an exothermic reaction, but this one has a much larger activation energy and a smaller change in energy. But still, since the reactants are higher than the products, it's still exothermic. And so delta H, which we're going to get into, is enthalpy. But delta H is negative here for exothermic because you're decreasing in the amount from the reactants to the products. A couple other things to look at when you're looking at these is, so that's for the forward reaction. You could also be asked about the reverse reaction. If it's exothermic in the forward reaction, it will be endothermic in the reverse because the new reactants are at a lower spot than the products for the reverse reaction. And of course, the activation energy then will be from the reactants to the top of the hump. And so the activation energy for the reverse reaction will be larger in this case than the forward reaction. Don't forget that endothermic reactions, if you're looking at it from the forward direction, you'll start lower and end higher. So here's kind of in terms of the bonds that are breaking and forming. Energy must be put in to break bonds, so that means that the delta H is positive there. You must use energy to break those bonds. Okay. Then when you're forming new bonds, energy is released, and so this part, the delta H, is negative. And then the energy change is the difference overall, and that's the delta H. And in this case, this is an exothermic, so overall it's negative. That means it released more energy than it took in when it was breaking, and that's a really important concept. Again, so since this is negative overall, that means when new bonds are formed, that's releasing more energy than it took in to break the bonds. Now, if you have a endothermic reaction instead, like this, okay? I'm not going to draw it like a box like they did, but it's endothermic. The reactants are at a lower energy than the products. That means that the energy used to break the bonds must be greater than the energy released to form the new bonds, leading to an overall positive energy change. Let's review catalysts really quick. Catalysts speed up reactions by lowering the activation energy. So there's our uncatalyzed. Catalysts will start at the same energy and end at the same energy, but they lower the activation energy barrier. So the biggest thing you need to know for this one with catalysts is that delta H, or the change in overall heat energy, is not affected by the use of a catalyst. Not changed. There you go. Okay, so let's look at an example of drawing a energy diagram like this. So if the reactant's energy is at 40, okay, the overall change in energy is negative 15, so that means it must be down at 25. So that means that the products are at 25, the reactants are at 40. The activation energy is 50, so that means it must be 50 higher than the start, so it must go up to 90 there. That. And so when there's our diagram, the product's energy is at 25 kilojoules per mole. The activation energy for the reverse reaction is the difference between the products and the activated complex, which is 65 kilojoules per mole. And then it says using a dotted line showing the curve of the same reaction with a catalyst, so you want to show it at a lower activation energy. Doesn't specify where, but starting and ending at the same spot. Okay, another example, methane combusts according to the following equation. It gives you the negative delta H. I recommend annotating the questions whenever you see something like this and just, okay, negative delta H, that means it's exothermic. All right, now at 25 degrees Celsius, very little carbon dioxide or water is produced after a few hours. Which of the following diagrams could help explain why the reaction is not producing yield and why? Well, so exothermic, right? So both of these are exothermic, which is good. But the biggest issue is, so why isn't the reaction happening even though we have everything else that we need? And the reason will always be, whenever you're seeing these types of questions, it's always going to be the large activation energy. Okay, so diagram 2 is the best diagram. Diagram 2 has a larger activation energy than diagram 1. It's your evidence. And so having a very large activation energy means that very few of the particles at that temperature have enough energy to overcome the activation energy barrier and produce products.